In this lecture, as an application of the Riemann-Roch Theorem, indeed by using their consequences on the computation of the dimension of the Riemann-Roch spaces, we give the first stronger version of the weak approximation theorem that we call Strong Approximation Theorem. So let me briefly recall that what we have statement in the weak approximation theorem. So in the assumption, we suppose that we are given our pairwise distinct places. Let me denote them by P1 up to PR. And we are given some functions. They are not necessarily equal to each other. And for given integers denoted by n1 up to nr, we know the existence of the function we can say that it is in some sense close enough to given functions, or the valuation of z minus xi at pi, this given distinct place, is exactly can be described by this given integers ni. In the stronger version, what we add is that we suppose that we are also given another place q. And in this case, depending on this place, we can also see that this function also doesn't have any pole at these given places. So its valuation at pi is always positive whenever p is not an element in these given places. In order to prove that, first let me fix the notation. And briefly we denote VPI by VI. And we introduce a set that contains functions such that they have no poles at these given distinct places. And probably in the discussion session or in one of your homework questions, you will verify that indeed this is a subring of F that contains K and lies in F properly. And like in the proof in the weak approximation theorem, this proof, the proof of the stronger version, is also technical. So first, by using this notation, we need to prove 3 lemmas. And in the first lemma, we suppose that, again, we are given our distinct places. And we are given non-zero function x and integer z, integer s. Then there exists a function u in O. By the O, we mean this ring. Such that u minus x evaluation of u minus x at p1 is strictly bigger than v of x, v1 of x, and other valuation at other places, distinct places, its image under the corresponding valuation ring is bigger than or equal to this given integer s. And in order to prove this statement, first let me set the integer which denotes the valuation of x at 1, and let me set the divisor whose support contains these distinct places p, i's, and q. And here c is the same. Here c denotes the valuation of x, and s denotes the given integer, and n is a natural number. And later we will see that we will need to choose it large enough. But for the moment, with respect to this divisor, if we consider its Riemann-Roch space, and if we consider a function inside of it, we know that its valuation at 1, so by definition, is bigger than or equal to minus valuation 1 of a. This is equal to c. And by the setting, we know that this is v1 of x. And first we can observe that v1 of u minus v1 of x, which is v1 of u over x, is bigger than or equal to 0. And on the other hand, again, if u is a function in the Riemann-Roch space of I, again for the other valuations at vj, here j is different from 1. V of u is bigger than of its valuation at s, so bigger than or equal to s. And our claim is that every function in this Riemann-Roch space gives us the desired property. And in order to complete the proof, yes, I mean, this says that we have already get this condition. In order to complete the proof, we need to see that u minus x has valuation strictly bigger than of v1 of x. And in order to see that, we will consider a k-linear map from the Riemann-Roch space to residue class field, which is determined by the first place v1, which maps the function u to evaluation of u over x at p1. And indeed, this definition makes sense thanks to this observation, because this observation tells us u over x indeed a function in OPF, valuation ring OP1, and its image is not going to be infinite by the definition of the residue class map. This is k-linear. And if we have k-linear map, the first thing we can check is its kernel. And our claim is that the kernel, indeed the Riemann-Roch space of the divisor, which only differs from its coefficient, only differs from at the first place at A1. And let me denote it by B. And to see this equivalence, let me write the definition of the kernel. So that means we want to consider the functions whose images are the identity of the residue class field. So that means U over X is element in P1. By the correspondence of the valuation maps and the places. Indeed, that means U over X has valuation which is strictly bigger than 0. And by the properties of the discrete valuation map, indeed we can see that it contains functions U whose valuation at P1 is bigger than or equal to C plus 1. Here C denotes the VP of X. And that means they have almost the same poles and zeros, but its zero order is C, at least C plus 1. So this is why it lies in AP, and that indeed it shows us the kernel phi is equal to the Riemann-Roch space of B. And by the first isomorphism theorem, this quotient space lies in FP1, and we can also consider an isomorphism if n is large enough. So in other words, we can say that if phi is onto, and only if this is isomorphic, or so if this is isomorphic, so both of them are the vector spaces over K, so they have the same dimension over K. And we define the dimension of the residue class field. I mean, by the definition, it is already degree of P1. And here's, okay, we say that n should be large enough. If n is sufficiently large. Because otherwise we can get trivial spaces on the left-hand side if the degree is negative. So this is why we want to suppose this, we want to consider this condition. And if phi is onto, and we can choose, of course, n is sufficiently large, or as large as possible. And this makes phi onto, and thanks to this property, we can consider the pre-image of 1. So here 1 denotes the multiplicative identity, or the field in, the base field in K, or the full constant field K. So that means U over X plus P1 is equal to 1 plus P1. And indeed, by making computations and again by using the properties of the discrete valuation map, by the way, I'm sorry, I promised to use this notation shortly, but each time I again wrote it in a long version. And by the V1, what I want to mean is VP1 or the VPI in general. And indeed, it shows us if we choose U from this Riemann-Roch space, and if n is large enough, we can also get the second condition. I'm sorry, first condition that U satisfies.